everyone, in this video we are going to discuss radioactive decay. So what we really want to do here by the end of the video is be able to describe what an alpha decay, a beta decay reaction are, so both of those, and then we also want you to be able to describe what a radioactive decay series is. So let's start off with the easiest, which is an alpha decay reaction. So number one, alpha decay. So when we say we have an alpha decay reaction or something like this, or an element has undergone alpha decay, what that means is it creates an alpha particle as a product. So a classic example of this is if you start with uranium-238, which we know has 92 protons, so that's our reactant, and then it spontaneously decays to create thorium. So now thorium has 90 protons, and it has a mass number of 234, and then the last thing that we would fill in is to complete this reaction, we need to fill in this product, because right now it's not balanced. Our mass numbers don't equal each other, and our atomic numbers don't equal each other. So in an alpha decay reaction, you always have to put your alpha particle right here. And so then what you would do is you would check to make sure it's completely balanced. So we see that we have 90 plus 2 on the bottom here, so we have 92, and then on our reactant side we also have 92, so that balances out. Then on our reactant side we know we have a mass number of 238. On the product side it's 234 plus 4, which is also 238. That also balances, so this is a good reaction. So this is a classic example of an alpha decay reaction. So now a different example of a decay reaction would be called a beta decay. So beta decay is when you release a beta particle or an electron as a product of a reaction. So we'll just draw it out here as an electron like this, which is what the beta particle is, and again it's as a product. So a classic example of this is if we take the thorium that we just established, we just created from the spontaneous decay or the alpha decay of uranium-238. So let's start with thorium here, which is the 234 with 90 protons. And this is going to spontaneously go through beta decay. So what happens is then it turns into what's called protactinium. Protactinium, that's an element I don't say very often. So Pa, protactinium, and that has 91 protons, and this also has a mass number of 234. So the only way you can balance this reaction is by putting a beta particle right here. So you have an E, a 0, and a -1. So this is also an electron, okay? Then you always check it. So we have a 90 for our atomic number on the bottom here, 91 plus a -1, so really 91 minus 1, we end up with 90, so this is balanced, perfect. Then we check the top, 234 on the reactant side, and then we have 234 plus 0, also 234 on this side, so this is also balanced, so we have a good example. So now I'm going to let you try one, because it's very, very important to make sure that you can still balance all types of equations, regardless of whether or not they have an alpha or a beta particle in here. So what I want you to do is balance the following reaction. So I want you to tell me what the reactant is here, and I'm going to give you the two products. There's just one reactant. So you have a proton and you have an electron. So what is this right here? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. Don't worry about it. We'll work through it together. So the first thing you do is you add up your subscripts, okay? So our atomic numbers. So let's use our standard isotope notation. So we're trying to determine what A, B, and Z are. So we're going to look for A first. So A is going to be equal to the atomic numbers on the product side. So the sum of them, I should say. So we have 1 from the proton and then -1 from the electron. And so we have a 1 plus -1, that is definitely going to be equal to 0. So our atomic number of our element Z is going to be 0, or particle Z, I should say. And then we have a B, so this is going to be our mass number, so this is our superscript. So for our proton it's a 1, for our electron it's a 0, so 1 plus 0 is going to be equal to 1. So now we know that we have a 1 on the top, we have a 0 on the bottom. We know that the piece on the bottom, or A, provides our identity. So as soon as you see a 0 on the bottom and a 1 on the top, hopefully your brain is screaming at you, it's a neutron, it's a neutron! And so this is just a very, very classic example of a neutron spontaneously decaying to create a proton and an electron. Okay, so that's a good example. You have to be able to balance these equations. You need to be able to do it. If you can't do it, you're not going to do well on this exam, especially in this portion. Okay, so get this skill down. So now, let's talk about the last thing I want to introduce here, which is called a radioactive decay series. And so I started to show you a series here in our first two examples of an alpha and a beta decay. So we started off with uranium-238. It spontaneously decayed to create thorium, and then thorium spontaneously decayed through beta decay process to create protactinium. Okay, so this is just the first two steps. So what a series is just a radioactive decay mechanism. So a radioactive decay mechanism that begins, and this is the important part, that begins with an unstable element and ends with a stable element. And that makes sense, right? If you think about it, if you have something that's unstable, very reactive, it's going to go through its process until you get to a product that is stable, right? So you start unstable, you get to stable. So let me show you this example in a little graph here. So this is the radioactive decay series of uranium-238. And so just like we saw in the very beginning, we see that uranium-238 spontaneously decays through alpha decay to create thorium, all right? So you see how I'm going from the upper right-hand corner to the lower left-hand corner. And so whenever we have an arrow like this, that is indicating that we have what's called alpha decay. Okay, so a downward arrow is alpha decay. Now, if we have a downward arrow that goes from the upper left-hand corner and goes down to the bottom right-hand corner, that is going to indicate beta decay. So the beta decay in this graph is blue, and the alpha decay in this graph is red. And so what we can see here is it starts off with uranium-238, and it goes through alpha decay to thorium-234, then beta decay to protactinium-234, then beta decay to uranium-234, then alpha decay to thorium, then to radium, then to radon. And so now hopefully right there that red flag went off again. You're like, I've heard that before. Because remember we talked about it in the module, The Air We Breathe, when we have these indoor air pollutants in our basement. If you ever have uranium in your basement, you are definitely 100% going to have radon because it spontaneously decays from U-238 and U-234 all the way down to radon. But then it continues on. And remember, radon causes really bad lung cancer, so that's why it's an issue and why we talked about it. But regardless of that, it continues on, and it goes on and on and on all the way down to the very, very bottom down here when we are finally able to create lead, or lead-206. And so now lead-206 is actually a stable element. And if you recall from previous videos, as long as we have an element with an atomic number less than 83, it's possible that it could be stable. If you have an atomic number of 84 or greater, you are 100% going to be a radioactive element. So at some point, it's going to go through some kind of radioactive decay process. In this course, we're only going to look at alpha and beta decay. All right, that's all I've got for you today. Take care of yourself. Drink water.